everybody. Today I want to continue explaining about the structure and evolution of stars. Let me share my screen. Yeah. In here, we can say that the maximum mass of the main sequence stars is around 100 or 120 solar mass. Here you see the Eta Carinae. It has a binary system of very massive stars, and it is from a very massive molecular clouds that stars lose mass in strong stellar winds in very massive stars. We can see that if we have more massive cloud fragments into stellar pieces during the stellar formation, we will have more massive stars. And dramatic mass loss, major eruption in 1843 created double lobes in Eta Carinae, as you see here. It has from a very massive giant molecular clouds, and then they have two massive stars, as you see here, and then they want to explode. Then we have minimum. What is about the minimum mass of the main sequence stars? That it is around 0.08 solar mass. At masses below 0.08 solar mass, stellar progenitors do not get hot enough to ignite a thermonuclear fusion. So here we have brown dwarfs. As you see here, it is brown dwarf and it is the other bright and giant star. And we can say brown dwarf are not a star because they do not ignite hydrogen. So we do not call them stars. And for brown dwarf, we can say that it is hard to find because brown dwarf, because they are very faint and cool, and they emit mostly in the infrared. Many of the brown dwarf have been detected in star-forming regions like the Orion Nebula. You see here Orion Nebula in visible light, and you cannot see any brown dwarf. But in infrared, you can see brown dwarf like this. And brown dwarf, they have low metallicity and low magnitude, and they are very faint. When the mass of the molecular cloud is low, we have brown dwarfs, and they won't ignite hydrogen, and then they won't be a star. We can observe them in infrared. And I can say that our sun won't be a brown dwarf. Maybe some of you think that it will be brown dwarf, but our sun will be white dwarf, not brown dwarf. And we have different kinds of brown dwarf, as you see here, L dwarf, T dwarf, and Y dwarf. And you see the mass of them and the size of them, or we can see that the largest of them is the size of the Jupiter. And you see their temperature 3000 to 1500 Kelvin, and then 1500 Kelvin to 500 Kelvin for T dwarf, and for Y dwarf we have 500 to 250 Kelvin for the mass of around 30. for white dwarf. And we have zero age main sequence. And here I can see that here you can see brown dwarf, they are here, but white dwarf, they are here. White dwarf are hot, but we cannot see them. They have low luminosity and high temperature. But brown dwarf, they have low temperature and also they have low luminosity. We cannot see them in visible light. And what about the zero age main sequence? And you can see in here, this line, maybe we can say, is zero age main sequence. The temperature and luminosity at which a star has is they ignite hydrogen fusion in core. And for terminal age main sequence, here you see they have no hydrogen. They start to burning helium burning. They do not have hydrogen. And you see here terminal age main sequence and zero age main sequence, and this is main sequence. And here we have three types of stars lower than our sun, solar mass stars, and the stars that are massive stars. And the duration of a star's main sequence lifetime depends on the rate at which the hydrogen is consumed in the core and energy lost by radiation from the surface. The more massive a star, the shorter is its main sequence lifetime. And you see here that the stars which are lower than our sun, they just have a convection zone. They do not have core or a special radiative core. They just have convection zone. But for solar mass stars, we have a radiation core and convection zone around the core. But for massive stars, it is vice versa. We have convection core, but radiation region around the core. And maybe you think that in main sequence stars, we do not have any active things or active process, and they are monotonic. But as you see here, they are not monotonic. In somehow they are, yes, a straight line, but after a while you see that in convection zone they are active. This is for main sequence stars, for convection zone of them. And for main sequence stars, they have hydrogen burning stars, and they are in hydrostatic equilibrium. And finite supply of hydrogen is finite lifetime of the star. And you see again here zero age main sequence stars, and here terminal age main sequence stars, and here is main sequence stars. And you see that when the stars are larger, for example, they are in 30 solar mass, their lifetime is shorter, 5 million years. But as the stars become less massive, for example, 3 solar mass, they have 640 million years, their lifetime will be longer. And for these stars, like our sun, solar mass stars, they have 10 billion years. They are in the main sequence until they reach the terminal age main sequence. And here you see the hydrostatic equilibrium. If the rate of energy generation in the core slows down, gravity wins out over pressure, and the star begins to contract. This contraction increases the temperature and pressure of the stellar interior, which leads to higher energy generation rates and return to equilibrium. As you see here, we have gravity in and we have pressure out. Here it is in hydrostatic equilibrium, but when the star loses its hydrostatic equilibrium, it means that the gravity wins and the star collapses, and it cannot be in hydrostatic anymore. Here you see the evolution of the main sequence stars. Stars' lifetime, we show them with T, and it depends on energy reservoir or luminosity. As you see, the energy reservoir is M, luminosity depends on M to power 3.5. Here you see the lifetime T depends on M, energy reservoir, over L, luminosity. It's somehow approximately is 1 over M to power 2.5. Massive stars have shorter lifetime. As you see here, for example, massive stars with 25 solar mass, they have more surface temperature. They are in spectral type O. The luminosity of them is 80,000 solar luminosity, and the lifetime of them is 4 million years. But as the star lose their mass, as you see here, for example, 0.5, and the surface is 4,000, and they are in M spectral class, and the luminosity is 0.03 solar luminosity, and the lifetime of them is 700,000 million years. And also we can say in luminosity 5, luminosity class 5, we have stars in main sequence stars, and they burn hydrogen. Here you see the binding energy of the atomic nucleus. The general description of a nuclear reaction is I, as you see, R and Z plus J, R and Z. The J is mutual to K, A cos ZK plus ZL, AL and ZL, where AI is the baryon number or nucleon number or nuclear mass, and Zi is the nuclear charge. The nucleus of any element is uniquely defined by the two integer Ri and Zi. Recall that in any nuclear reaction, the following must be conserved. The baryon number, for example, protons, neutrons, and their antiparticles, and also the lepton number, like light particles, electrons, positrons, neutrinos, and antineutrinos. And the other conservation is conservation of charge. Be careful about that the antiparticles have the opposite baryon or lepton number to their particles. And the binding energy of the atomic nucleus, the total mass of a nucleus is known to be less than the mass of the constituent nucleus. Hence, there is a decrease in mass if a companion nucleus is formed from nucleons, and from the Einstein mass-energy relation, as you know, is equal to mc squared. The mass deficit is released as energy. This difference is known as the binding energy of the compound nucleus. Thus, if a nucleus is composed of Z protons and N neutrons, its binding energy is Q, Z, and N, approximately Z, MP plus N, M, N, minus M, Z, and MC squared. For our purpose, a more significant quantity is the total binding energy per nucleon. We can then consider this number relative to the hydrogen nucleus, as you see here, Q is Z and N over A. Thank you for your attention and see you next time. Bye.